Hello students of science. In this video we're going to talk about the driving force of reactions, why some reactions happen and others don't. And a big reason for that is entropy, a new concept we're going to be introducing here. Most chemical reactions, as we talked about before, are exothermic. They give off heat. Very big reaction like that, very exciting. They're also going to result in much more stable products. If you think of like after a campfire, you don't need to worry about taking care of that ash. It's not reactive. You don't need to worry about doing anything with it. It's already a very stable product. So here I have an energy diagram. My reactants join the product. Heat is going to be given off, like when you burn that wood, and the products are going to be much more stable than we already saw. And most reactions are going to occur spontaneously. Now, to understand why, we need to understand entropy, which we use the letter S for. That's a measure of the disorder or the randomness in a system. Here's a system right here with very low entropy. Here's high entropy. So a lot of disorder, a lot of randomness here, not so much here. Here it's very ordered and systematic. The natural process of the universe, it has a tendency to always go toward more entropy. So keep that in mind. Things are always going toward disorder. The only way for an endothermic reaction, something with more stable products, to happen spontaneously is due to an increase in the overall entropy of the system. So here I have an endothermic reaction where heat is going in. That is entirely possible that that could happen, but that must result in more disorder and more randomness in the system. Exothermic reactions, which we're kind of used to by now, those of course it's easy to see why those happen. They're losing energy going toward more stable products. Here's an entropy seminar. The results of a 5-year study in the laws of thermodynamics tends to go toward disorder and randomness. So entropy roughly correlates to temperature and states of matter. Gases are going to be highly disordered, a lot of entropy in there. Liquids are going to be less organized, more so than solids, which are going to be very organized. And when you reach the temperature at absolute zero, entropy is going to be zero. So please make sure you write that down and include the arrow. Entropy increases with gases having, of course, the most entropy. Solids and absolute zero compounds are going to be the least. Here I have different states of matter. That's solid, that's liquid, that's gas, and that's a very hot gas right there. Very low entropy there, more here, more disorder, more randomness, more disorder and randomness here, and of course the most amount of disorder and randomness there. Crystalline solid, when you move to a liquid, I'm going to be increasing entropy. Going to a gas, I'm going to be increasing it even more. So gases have the most entropy compared to a crystalline solid. Here you have something like ice, very systematic, very organized. Of course, you add heat, you're going to be getting water, a lot of disorder, a lot of randomness, so increase in entropy when you added that heat. The forming of a solution is also going to increase entropy. Here I have a system, I'm adding these different particles in there. It's increasing the overall order and disorder and randomness of the whole system because it's almost dissolving. This includes mixing of gases, mixing of liquids, and dissolving the solid inside a liquid. Here I have a solid and it's moving out. That is going to increase the overall entropy in that system because there's a lot more disorder and randomness. Also, increasing the number of moles is going to increase entropy. When we went from one large one to many, many, many small ones, entropy increased. So don't copy this here. I just want to show some examples of how you can determine if entropy increased or decreased. So here's 5 examples. I'd suggest pausing it and trying to see how well you can do on your own. First one, potassium chloride, that's going to go from a solid to a liquid. That one is going to be an increase in entropy because you're going from solid to liquid. The way to look at this is you want to start with the different states of matter. Here I'm going from solid to liquid. Next thing you're going to do, if there's no change in that, you're going to look at the number of moles, then did something dissolve. So this one here is going to be an increase because I went from a solid to a liquid. Entropy increased. Solid to liquid to gas. More entropy, more randomness. Let's look at the next one. Nitrogen gas plus hydrogen gas is going to make ammonia, in this case in the gaseous form. So we don't have any changes in state, so we can't do that. So now we need to look at the number of moles. On the left here, my reactants, I have 1 plus 3, so I have 4 total moles, and in the end I'm going toward 2 moles. So I'm going from 4 to 2. That's actually going to be a decrease in entropy because I have fewer number of moles of substance. Looking at our next one. Potassium chlorate is going to break down to form potassium chloride and oxygen. So let's look at my changes of matter. I got a solid, and a gas, but it's hard to tell when one's a solid and one's a gas. So let's go toward our number. Here I have 2 moles of potassium chlorate, 2 moles of potassium chloride, and 3 moles of oxygen. So I have 5 over here and only 2 over here. Going from 2 to 5, well, that's definitely an increase. I have way more moles of substance left here than I did at the beginning. A lot more disorder and randomness with that. So that one will be an increase in entropy. Next up, I have a hydrogen cation plus this compound right here is going to form this liquid compound here. This one's going to be a little bit tricky because I have aqueous, aqueous, and liquid, but this one's going to be a decrease because I have 2 moles of my reactants and only 1 mole of my products. So that's a decrease in entropy. Last one, water going from a gaseous to a liquid state. Here, I'm going to be going backwards on here. Entropy in this case is going to be decreasing because I'm going from gas to a more ordered liquid. So to tie all this together, entropy plus enthalpy plus temperature, we need to use Gibbs free energy. Gibbs free energy is going to tell us for sure whether or not a reaction is going to happen or whether or not it's not going to happen. So the equation that you need to write, delta G, and that's the degree sign saying that it's at standard state, is going to be the change in enthalpy, delta H, minus the temperature times the change in entropy. A lot of words here that sound alike, entropy and enthalpy, but got to make sure you're getting this one here. So this is my equation for Gibbs free energy. If my overall delta G is negative, the reaction is going to favor the products. More or less, this means that reaction is going to happen. So here we have a negative delta G. That reaction is going to go forward because we're going to be decreasing the amount of free energy in the system. So in the chemical equation, this would go to the right in the chemical equation. So when you have it written out, it would happen. If that delta G is positive, the reaction is going to favor the reactants. Well, remember, reactants are what you start with. So more or less, this is saying that reaction is not going to take place if the delta G is positive. So it goes to the left or it doesn't happen at all. So reaction going forward, this is when the delta G is negative. Reaction going backward, when the delta G is positive. And of course, if the delta G is 0, we would say that reaction is currently at equilibrium. Nothing is really going to be happening. So let's take a look and sort of combine our concepts of endothermic and exothermic and entropy increasing or decreasing. So remember, here's our equation for free energy. Remember, if it's going to be a negative one, the reaction will go forward. If it's going to be positive, the reaction will go backward. So here I need to start whether or not it's going to be endothermic or exothermic, and I'm going to be subtracting temperature times the change in entropy. If this overall result is going to be negative, it's happening. If this overall result is going to be positive, it's not happening. So an exothermic reaction here, where the entropy is going to increase, those are things that are going to be favored. That's going to make this number negative here, and I am going to be increasing my amount of entropy. At all temperatures, this reaction is going to go forward. I'm going to have a negative delta G. This reaction is going to happen. And remember, we can get an endothermic reaction to happen. However, you need to have high enough temperatures for this to work. This change right here, this temperature, that needs to be very large so that when it subtracts from this, you're still going to get a negative delta G. So only at high temperatures will you see an endothermic reaction, one that sucks that heat out, happen because the entropy of the universe is essentially going to be increasing. Something like a cold pack would be a good example of this. Cold packs aren't going to work at all temperatures. It needs to be warm enough for a cold pack to actually go through that process. Next up, an exothermic reaction where entropy decreases. This is only going to work when that T times the change in the entropy is low. And of course, if we have an endothermic reaction that decreases the entropy, two things that the universe does not like, that is never going to happen. That delta G is going to be positive, therefore that reaction is going to go backward or not take place at all. Make sure you have this table and you can understand this, and we'll kind of work our way through some examples.